Hi, I'm Donna Dietz. Pysheaf is a Python package written by my colleague and also husband, Michael Robinson, and it's available on GitHub, and that's what we're going to talk about today. About a year ago now, this guy right here invited Michael and me to a summer school in Osaka. Now, and the others participated. Here's me, here's Michael. We were all participating so we could think about the nature of human consciousness from a scientific perspective. We were brought in, Michael and I, to add some mathematics to the discussion by way of sheaves. My point was to bring to this discussion the fact that this isn't my area, and just like most of the researchers there, I know how to program, but I don't know much about, didn't know much about sheaves. So my goal was to ask all the questions a beginner would ask and grapple with this from a fresh perspective. As Michael and I continued this back and forth over several months, these various examples arose, and I asked him more questions about the software and posed various toy problems. This talk is a summary of hours of talks between me and Michael and many hours of lab time where we worked with the participants using Google Colab. All that code is available for your use. At first, our discussions were a little open-ended, but I really wanted to make it concrete. How do I use Pysheaf to model my problems? My goal is that by the end of the talk, you'll be inspired to give it a crack yourself. Please go ahead and grab these slides. They'll give you access to these slides as well as other resources, all the resources we gave the participants in Japan, including videos and whatnot. Okay, and I'll give this QR code at the end again. This is the QR code for specifically the materials we used in Japan. Okay, so first of all, why sheaves? Well, sheaves allow us to compose different models. We may have different boundaries on different parts of the model. We want to combine boundaries. We want different types and levels of interaction, different levels of the problem that need to interact. Noisy real-world data. Okay, so I want to know, what are the rules? What types of problems can we solve? Not really everything, but kind of. Express existing problems in a new way. You still have to solve the problem yourself. Your workflow is going to be, first you build a sheaf, you're going to pick an assignment, and then you're going to optimize. You have to really rethink your ideas about the flow of information. It's not the way information flows in the physical, real world. So what do we need? We need a directed acyclic graph. We need nodes that represent sets and arcs that represent functions. We need path independence for functional compositions. And if you select all this correctly, you have what's called a consistent assignment. Okay, so I'm going to give you, first of all, if you don't remember what a directed acyclic graph is, this is what they are. Notice that you can't double back on yourself. If you have to follow the arrows, you can't get back to where you started from. Okay, so there's your directed acyclic graph. Here's the most simplistic sheaf I can come up with. So you notice there's the independence of functional composition. In other words, if you want to go from A to C, it doesn't matter which path you take, you'll still get to the same result by composing the functions. And if you mess this up, you'll get an inconsistent assignment. You could tell the program, you could tell Pysheaf, hold A at 700, but I'm going to allow B and C to range between 1,000 and 2,000, and then we will end up back to where we started with our consistent assignment. So Pysheaf can do that for us. Okay, all right, so first non-trivial example. I'm going to use it to reinvent least squares regression. Each point of data is going to be a node, as will the line of best fit. You might instinctively want to make the arrows go the other direction because we know points determine the line, but this is what I meant about rethinking how data flows. M and B are what's free to move in the real world, so they can be real values, and those M and Bs push out estimates to the point. So these data structures which hold the data are also going to be used to hold the estimates for y prime and the difference between those estimates and the stored values. We're going to square them, add them, take the square root, because after all, we're just reinventing least squares regression. And that thing that we're now going to minimize, you might call an objective function. We'll call that the consistency radius. So that is the thing we're going to optimize. Okay? All right, so we can do the same thing with polynomials, the same least squares trick that we did with polynomials, but this brings in another important point, and this is to demonstrate that as you keep refining your model, when you hit upon the right model, the consistency radius tells you that. and the fact that the model becomes stable tells you that. So I'm starting off with something really naive, just 6 points from a parabola, and then I'm going to say, please fit a constant, please fit a line, please fit a parabola. And as I keep asking my model to become more complex, something cool happens. So notice here, this is just fitting a line. It has a pretty poor consistency radius. So 147 is a really poor consistency radius for this context, okay? But once we hit upon the right model, our consistency radius drops to almost 0, because obviously this was a perfect, this can be fit perfectly. All right, but notice when we now say going from a parabola to a cubic, then the model does not actually improve, right? So the consistency radius stays really low, and then the solution is actually stable because this solution is actually the same as this solution, because the new coefficient is just 0, and so we're good to go. So that is really good reinforcement. That's great about Pysheaf, and using consistency radius to calculate when you get to your answer, it gives you that reinforcement, knowing that you got to the right answer. Okay, Titan example is an example that is only slightly different from the other ones, but if you recall a while back, this submersible exploded. It was tragic, but I was surprised at, honestly, why we didn't find it sooner, why humans were having so much trouble finding this thing, because I said, I know there's underwater listening stations. And for a really simplistic model, even if like 6 listening stations could tell you where, they know where they are, and they know what time they heard the explosion, so they should be able to reverse engineer where the Titan was, when it blew up, and how fast the speed of sound is traveling in the water at that moment. That's, of course, making the assumption that it's consistent everywhere, and that's false, and I understand that. But this is just a really simplistic model, and if you want to look at the code, it's all at that link I showed you. One of the great things is you can play a game now. We had the participants do this, like hide the Titan somewhere else, explode it at a different time, and take that output and give it to your colleague and have them find where you hid the Titan. Okay, so one of the great things about Pysheaf is that you use the same exact code to solve the forward problem as you use to solve the inverse problem. You just have to change the flags on which pieces of information are known and which pieces of information you're looking for. And so with very little change, you can use the same code for both forward and inverse, and also hybrid. Okay, next example is fox hunting. This is just an amateur radio hide and go seek with a hidden radio transmitter. This is one of our kids, Edwin, obviously younger in this photo. But for this model, we're going to combine 2 types of distances. We're going to assume some sensors can only tell us the direction in which the hidden transmitter is, and this is the type of antenna he's holding right there. As some antennas, just your standard antenna on a handheld radio, is going to give you a sense for how far away that item is, because when it's louder, it's obviously closer, and when it's harder to hear, it's obviously further away. So we're going to combine these 2 distance measurements, and what Pysheaf allows us to do is, rather than having 2 different functions to minimize, we just multiply one by a constant, add them together, and then we've got one single objective function that we're trying to minimize as we progress. So that's just a matter of experience what that multiplier is, but you have to explore it for your own exercise. Okay, but basically everything's being optimized simultaneously. All right. A circuits example. I like this example to demonstrate how you can optimize over zeros and ones instead of over real values. So under the hood, your optimizer is the SLSQP optimizer. You can swap out a different optimizer if you want, but Pysheaf comes with SLSQP as the default. And one of the great things is it allows us to set bounds. Say, I want my solution to be only between 0 and 1. And then we use other tricks to keep the solution away from 0.5. And what you end up with is an optimizer that actually gives you answers that are only zeros and ones. So that's pretty cool. And again, I'm going to use this just briefly to emphasize that information does not flow in the model the way it does in the real world. So electrons are going to go from left to right. So the flow of time is from left to right in the circuit diagram. But the way the information flows within the sheaf is it begins at the components and pushes out to the wires. And that's pretty cool. That's a whole different paper that Michael wrote, but it's just a really cool takeaway here. Okay, this Classification example. I do this every year with my data science students using scikit-learn. But I just decided to come up with some kind of naive model and try to do it with sheaves. And after I split into the training data and the testing data, I got like 90% success rate. Again, really stupid naive model, but that's part of the thing with Pysheaf. You're still building your own model. If it's a dumb model, it's still a dumb model, even if you're using Pysheaf. Okay, so anyway, I just did it as a proof of concept. Okay, diffie-q, don't read this. Okay, this is what the solutions should look like because I created the problem by gluing two functions together. I wanted one to land on the integer solution and one to land on an irrational value. I wanted to go between the zeros there. And so I just did the standard numerical computing tricks, and these are the standard formulas you would get if you're doing this sort of thing with burden and fares or whatever. And so I just glued them together. This P0 is the same as this P0. I just kind of shifted them on the slide. And so this is what the solution looked like, pretty good. You can see there's some residual, the residuals jump up at the join point, okay? And last example, okay, so I said we needed path independence, but what if we violate it just a little bit? So I came up with this example of a road trip from Nova Scotia down to Miami, but I wanted to give the driver a little bit of freedom to maybe avoid Boston or Hartford if they wanted to, but I'm still making the driver go through Providence and I'm still making the driver go through Philly, okay? And so what the whole takeaway for this is to stress that if you have a very tall digraph that's got a very long path in it from top to bottom, then what you're going to need to do is split it at the pinch points if at all possible, because this becomes computationally unwieldy very, very fast. It's not the fact that there's a lot of nodes, it's the fact that you're computing all the possible paths through. Okay, so it's the fact that the height of the digraph is what's causing this to blow up computationally, and it's not the number of nodes. So I wanted to kind of stress that, and if you get the slides, there's a longer explanation as to why that happens. Once you understand what the code is doing, it will be dreadfully obvious why you don't want tall digraphs. Okay, and so that's the end of that explanation. Please take the slides and reach out to us if you have any questions. Definitely play with the code. It's all freely available, and so you can just use it. It's on Google Colab. You don't even have to set anything up. You can just start playing with it. Okay. Any questions? Just reach out to us.